Good afternoon, everyone. Assalamualaikum warahmatullahi wabarakatuh. Welcome back to the second section, second section of our UNDIP Global Classroom program atau our UGC program for the course Vector Calculus or Fourth Calculus, at the Department of Mathematics, Faculty of Science and Mathematics, Diponegoro University. I am Jovian Pratama, lecturer and coordinator of the Vector Calculus course. Okay, today we are pleased to continue our guest lecture session with Dr. Mohd Ali Khameini Ahmad. Hello, Doctor.
Hi, so thank
Okay.
you. Can you hear me?
Yes, yes.
Okay.
Okay, Dr. Mohd Ali Khameini Ahmad from Universiti Teknologi Malaysia. In the previous session, Dr. Ali delivered an excellent lecture on surface integral. Yeah, and today he will continue with another important topic in calculus. That is green theorem. Yeah, green theorem is one of the fundamental theorem in vector calculus, connecting line integral around a closed curve, with double integral over a plane region. This theorem is also closely related to many applications in physics and engineering, also fluid dynamics. We are truly honored, to have Dr. Ali once again sharing his knowledge and experience with us today. I encourage all students to actively participate, ask questions, and make the most of this valuable opportunity to learn from an international scholar. Okay, without further ado, it is my great honor to invite Dr. Ali, to begin today's lecture. Okay, the floor is yours, Dr. Ali.
Okay. Thank you very much. Thank you very much. So let me continue with the Green's theorem then. Okay. All right.
Sorry, Dr. Ali, your voice
Okay.
is a bit uh,
Can you
low.
my voice slow? Can you hear me? Test one, two, three.
Okay, it's better.
Now better.
Yeah,
What happened? Let me test one, two, three. How about now? Can you hear me?
yeah, it's clear. It's clear now.
Okay. All right. Okay. Yeah, great. So yeah, let me continue this lecture on Green's theorem. So before that, let me share my screen so that I can show you my writing about Green's theorem. Right. Can you see my screen now? Stop sharing.
Not yet now.
No, it's not working. Okay. How about now? Can you see the screen?
Okay, we see.
Okay. Hmm. Oh, okay. This one. Okay. So let me just continue. So with our lecture number 2 of my sharing here. So it's a great pleasure for me to have this opportunity also. So hopefully I will share you something so that it would benefit you, all of you. Yes. So yeah, let me just talk about Green's theorem here. Green's theorem. As mentioned before, it's very old topic here. It's related to many application. Indeed, it come from application, how this Green's theorem works. Some people working in physics there, in electromagnetism. So, but mainly here, I will talk much on mathematical part. Okay, mathematical part. Okay. So let me just state you what is Green's theorem, and then I will what we call here, we will explain the term then one by one. Okay. You can see now my screen. Is it looking well in your side?
Yes, Dr. Ali.
Yes. Okay. So what is Green's theorem? So Green's theorem will relate as mentioned by Mr. Jovian there, Dr. Jovian there, about the circulation and also surface integral. I mean the double integral. Okay. So let me write it. The formulation of the theorem here. Let C be a curve. Okay, be a curve. C be a curve with positively oriented. In our case, if we look from this side, it is not counter. It's counter. Yeah, counterclockwise. I mean, counterclockwise. Okay. And then what else? It be piecewise move. And it should be, the main thing here should be simple and closed curve. Mhm. Simple and close in on the plane. On the plane. Okay. Right. So this is the first assumption we need to have. Then let R be the region bounded by this C. By C here. Okay. Bounded by C here. If, so we have this assumption, if we have P and Q with the component of the vector field has continuous partial derivative on open region R here, then we have this Green's theorem formulation, which is if you want to compute this circulation, the line integral f dr, it is equal to, you are computing the double integral of this partial q partial x minus partial p partial y. Okay, dA. Okay, so far so good. Yeah, clear? This one. Okay. So this is the Green's theorem. Okay, so what it means. So what nice here, it is one dimensional here, C, has relation with two dimensional here. Okay, you have this relation of what we call here one dimensional punya integral with two dimensional punya, I mean single integral with double integral here. Okay. Right. So that will be the statement of Green's theorem. So let me just explain a little bit one by one about this assumption here. So first, you need to have C, which is simple and closed. Okay, this is simple and closed curve. Okay, simple and closed curve. So the orientation should be anti-clockwise here. Okay, the next things. So what is simple and closed? So you see that simple mean there is no intertwined there. Okay, something like this one. This is not simple. This curve is not simple. Okay. Or you have something like this one. So this is not simple also. Okay, meaning that you only have one region there. Okay, and then what is close? So close meaning you can come back again at the where you start. So something like this. So if you have this kind, simple and closed curve, so meaning that it is not unbounded. Okay, another way you can understand. Okay, dia dah mengajar. Okay, so if it satisfies this one, first simple and closed curve here, and then it is positively oriented. In our case here, we will look here as counterclockwise. Yeah, okay, counterclockwise on the plane. Okay, so that will be the things about the curve here. So the piecewise smooth here, meaning that, for example, if you have something, you have this line, and then you have this curve. Yeah, this is also something like you have several, made up of several curves. For example, this is C1, this is C2, C3, and C4. So this will be also uh, included in our case here, if it is piecewise smooth here, meaning it is continuous here from this one, and then from another line here, it continue. Yeah, it will go without any gap here. So it is what it means by piecewise smooth there. Okay, so if the C is satisfied these properties, and then you also have what? What is the R here? The region R here is the things that bounded by this C. So this will be our R. This is our R. Inside the R. R. Okay, R. So this will be R also. This is our R. Okay, this is our R. Okay. So this will be our R here. So anything inside, okay, inside bounded by that closed curve, we denote by our region R here. Okay. Yes. Okay. Any question? No. No. Okay. So now, next, if we consider this vector field, if F in the plane that x, y equal to what? P x y I plus Q x y j. Okay. So if this vector field has continuous partial derivative, x, specifically if P and Q has continuous partial derivative on open region R. Region R, okay. Then what does it mean? It meaning you have partial Q, partial X, partial Q, partial Y, partial P, partial X, partial P, partial Y is continuous on, so this is what it means. This continuous on R, okay, continuous on R. Then we can apply this Green's theorem calculating the circulation. dot dr equal to partial derivative here over r partial q partial x minus partial p partial y dA. Okay. Example. So let me go to example to look whether this is uh to look whether this is applicable. Okay. So now let me consider this simple Green's theorem. Example. So compute this one. F compute this one dr where f is given by this. I get it fully. So I have 3x minus 8y square I plus 4y minus 6xy j. Okay. Where the c here given by this one. C boundary of R bounded by x plus y equal to 0, y equal to 0, and x equal to 0. It's x equal to 0 here. Yeah. Okay. And then it's positively oriented. Positively oriented. Okay. Baik. So how can we compute this one? How can we compute this one? How we can compute this one? So let me check it whether what we call here C is first surely it is positively oriented here. It's stated there. And then what? What we need? We also have what we call here closed, right? Because you have a region bounded by that C, so it should be closed there. It's simple, so let me check it. So firstly, always try to visualize or sketch the C. Test 1, 2, 3. So you have what here? So you have x equal to 0, y equal to 0 line, right? So and then you have this x equal xy equal to 1. I'm sorry, this one should be 1. 1 here. This is x plus y equal to 1. 1, 1 here. This is line y equal to 0 and x equal to 0. So meaning that this is our C. Okay, so if I use different color. So I have this curve. Okay. All right. Baik. So surely this is simple enclosed, right? So I will see here the red color is simple enclosed. Therefore, meaning that you can apply this, what we call Green's theorem. Okay, Green's theorem here. So this is our C. And then it is oriented positively, counterclockwise here. Okay, counterclockwise. Baik. So what does it mean here? So if you want to compute directly the line integral, or mean the circulation there, is done here, right? Circulation here, C f dot dr. If you don't want to use the Green's theorem, you will compute what? You will have this C1, this is C2, this is C3, for example. So you will have three piecewise curve there, right? So you will have C1 f dot dr plus C2 f dot dr plus C3 f dot dr here. Okay, next. Now, if you try to integrate this one, you need to have these three piecewise. Okay, sorry. So from here, okay, from here, this one also equal to the Green's theorem that I mentioned earlier. So if you consider this region as R here just now, so you have this is R partial Q partial X minus partial P partial Y dA. Okay. Baik. So that will be the things. So how we can compute this? Okay. So let me just compute this one first. And then we will try to compute this one and compare the answer that it will be the same. Okay. So now what is P, what is Q? Okay. So our P is what? Our P, so we try to compute these things first. Our P is equal to what? Our P equal to 3x minus 8y square earlier, right? And then our Q should be 4y minus 6xy. And then you just differentiate lah. Find the partial derivative. U sub x, p sub y. So you differentiate with respect to y, this p sub y. Oh, let me write partial form. Partial p, partial y. You will get negative 16y, right? And then partial q, partial x. You will get negative, negative 6y. Okay, negative 6y here. Okay, negative 6y. Baik. So next what? So next is we try to compute this thing, partial q, partial x minus partial p, partial y. So partial p, partial q, partial x minus partial p, partial y should equal to negative 6y minus 16y, right? Negative 16y, which is 10y here. Okay. So now you will have these things. Double integral, we rest 10y here, dA. And then our region is, just now is this triangle, right? Okay, this is x plus y equal to 1. Below is y equal to 0. This one is x equal to 0. Okay. Baik. So next what? You just calculate lah the double integral kan. This one just you compute the double integral. So let I choose the order here. So what do we get? If I choose the order with respect to x first. So I will have 10y dx dy. Okay, and then I will find the limit of integration first with respect to x. So I have these things. One. So I will draw a line parallel to x-axis. enter here and leave here, right? To enter at x equal to 0 and leave at this line, which is x plus 1 equal to y, equal to 1 minus y. X equal to 1 minus y. And then from where to where you need to find this. Limit, you get from 0 to 1. Y equal to 0, y equal to 1. Right. And then, yeah, this one you can solve easily. So what do we get? 0 to 1, and then you need to integrate with respect to x first, kan? Then y, you get x, limit from 0 to 1 minus y, dy. Substitute everything here. You will get what? I will get then y, 1 minus y minus 0. You get 1 minus y there, dy. Okay. So finally, you will get 10y minus 10. Oh yeah, you can pull out outside 10, right? You get 10 there, 0, 1, y minus y squared. Dy should give you 10 y squared over 2 minus y cubed over 3. Limit from 0 to 1. So what do we get here? If you have the answer should be 5 over 3, right? 5 over 3, because if you calculate this one, you will get 1 over 2 minus 1 over 3. So this one should be 1 over, is it correct? I'm calculating here. Yeah. So this will be times 2, 3, 6, right? 5 over 6 there. 10 over 6 should be 5 over 3. Okay. All right. Okay. So far, yeah, this is just a double integral, okay, from your previous calculus course, I think. Okay, about the double integral. Baik. So far, so good. You can follow. Any question you want to ask? Yeah. Good. Okay. Okay. No good. So now let me compare with this double. No, there's line integral here. So how we can compute this thing, right? You need to compute one by one, right? You need to compute this thing, C1, C2, and C3. So you have three line integrals. Compared just now, you only have one double integral. Easy to compute in one sense, lah. In one sense. So let me just show you how to compute this C1, C2, and C3. Okay, so let me just copy this one, I think. Right. Copy this one. Then I will paste it at below. Okay. Okay, so now let me compute one by one. So first you need to compute this line integral C1 f dot dr. So what is it? So how we compute? I think you maybe learned already how to compute this line integral. This is a work done, or you can have circulation there. This is like circulation here. So you will have what? So you need to parameterize, right? You need to parameterize C first. So what is C1? C1 just y equal to 0. Y equal to 0, where you have x from 0 to 1 here. So how to parameterize C here? So our R here, C1 can be written also as follow. So T equal to what? The x component is T there, Ti plus 0, because y always 0 here, right? Y always 0 here. Whenever T runs from 0 to 1. So this one way you can parameterize, okay, the T1 here. Okay. Okay. And then you find the R prime T, right? You get 1, I. You get just I here. Okay, I here. Okay. Okay. Therefore, you will have what here? So these things is equal to, you have from 0 to 1 because our T is from 0 to 1 here. So you need to use this one. So F is equal to what? F is equal to, yeah, another way is you can write it in this form. So before I move to this form, so I can also rewrite this one in the differential form. C1 you have P dx plus Q dy. So this is another way to write this circulation. I mean the flow integral using this form, okay, in differential form. Okay, right. So from here you will find everything from here lah. Okay, so I will have what? So P is equal to what? P x y is equal to, so you just substitute everything this one. This is x in y here. So we have x equal to t, y equal to 0. So everything you see x, you just substitute t, y, you get 0 there. So you have 3x minus xy square. So our other, you will get 3t. Okay, 3t here. Wait. Whereas for q, xy, you will have what? Q is 4y minus 6xy, right? 6xy. 6xy. So y is 0. Here everything is 0 here. You get 0 here. Here 0. Okay. Right. And then next you just substitute everything inside here. You will get, let me write it here, this side. So what is dx dy? Is from here, okay? Because this is x, y. So you have dx is equal to 1, dt, dy is equal to 0 dt lah. So what left is just 0 to 1, p is 3t, dx is dt. And then this is a 0. Q is 0, dy is 0 here. So you compute this one, you will get what? 3t square over 2 from 0 to 1. Okay. So you will get at the end just 3 over 2. Okay, 3 over 2. Right. Okay. Right. So this will be the first integral. And then you need to do another integral. So you have two more integrals, right? Next, what? This one so far, okay? Clear?
Yes, Dr. Ali.
Okay. Oh yeah, okay. Thank you. So yeah, next is you need to compute the second one, kan? You will have C2 F dot dr equal to C2 Px dx plus Q dy. Okay, which is now our C2 is what? Come back again above. You will have this slanted line here, right? X plus y equal to 1. So anyways, remember C2, you need to parameterize R equal to what? So the x coordinate I can choose as ti plus, because you have x plus y equal to 1, so x equal to t, so y equal to 1 minus x, which is 1 minus t lah. 1 minus t, j. Okay? So here you see that t runs from 0 to 1 because you have x from, no, it should be from 1 to 0. Okay? It should be run from 1 to 0. 1 to 0. We should have t from 1 to 0. Okay? So we have this decreasing value of t here. Okay. So, or you can parameterize another way because you know this is the line, right? If you want to make it nice integral, this is you want to make it increasing value of t here. So this is x plus y equal to 1. So this is what? 0.10. This is 0.01, right? So how you parameterize a segment, line segment, right? So x here is equal to the initial point plus the end point minus initial point, okay? Minus x0 t here. Similarly, y equal to the initial point of y plus end point of y minus initial point of y here. So this one, another way you can parameterize this c here. So from here you have what? This is x0, y0. This is x1, y1. Okay. So you have what here? This one should be equal to 1 plus 0 minus 1 t, right? 0 minus 1 t. Whereas this one you will have 0 plus 1 minus 0 t. Okay. So this another way you can use. So instead of x here, I make it from y here. Y. I will make it y. So another way to parameterize this line segment is using this formula where you take the endpoint and initial point. Therefore, I will have what here? So let me write it here. So T C2 can also be written as follow. 1 minus Ti plus Tj. Now we have increasing value of T0 to 1. Which nice, which is a little bit nice lah to write in this vector function. Okay. So I have this one. So you just find the derivative. So this is x, this is y. Therefore, dx is equal to negative 1 dt. dy should equal to dt, right? 1 dt. Baik. From here, we have this thing. Next is what? Yeah. So let me write it here. X equal to 1 minus t. Y equal to t. The parametric form of the curve. And then you need to find P and Q, right? P, just recall again. PQX equal to 3x minus 8y square. And then in our case now, you have x equal to 1 minus t, 3, 1 minus t, and then y is t minus 8t square. Okay? And then you have QXY, which equal to 4y minus 6xy. So I will have what is y? T. 4t minus 6, 1 minus t, t here. Then you can simplify everything. You get 3 minus 3t minus 8t square. This one 4t minus 6 plus 6t square. Okay. Okay. Baik. And then from here, you just find the No, this is not green. I mean, just substitute back here inside, right? Everything. So meaning that all of this. So the second integral is equal to what? Second integral is equal to from 0 to 1. So P here should be these things. You have 3 minus 3t minus 8e square. And then you have dx equal to negative dt. And then plus q is 4t minus 4t minus 6 plus 6t square. And then you have dt, right? Yeah, dt for dy here. Okay. And then you can simplify. Okay, you can simplify. In some sense, you can factor out lah this dt. So you will get what? 0, 1. You get this is negative 3 minus 6. You get negative 9, right? Negative 9. This is positive 3. 3 plus 4, 7. Yes, 7. 3. And then this is 8 plus 6 should be 14. 14, 6. Huh? I'm sorry. 14t squared. 14t squared. Then you have dt. Okay. Then you just compute this one. So the final answer, this one should equal to what? If you try to compute, you will get 16 over 6. And 13 over 6 then. 13 over 6. Okay. 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 So far so good. Managed to follow this one. Hopefully. So hopefully it's, yeah, maybe somewhere I did calculation there. Please check again. And then the final should be 13 over 6. Yeah. Okay. You see that you have two integral you need to to deal with compared to when you deal with Green's theorem. Okay. So it's a bit lengthy and tedious work if we deal without using Green's theorem. And then if you compute the last one, the C3 FDR, so this one I will leave it to you to compute it, and then the final answer, this one should be equal to what? Just now I got 5 over 3, right? 3 over 2. This one should be 5 over 3. This should be 5 over 3. Okay. Okay. And then if you add up all of them, the answer should be equal when you compute using Green's theorem. Therefore, the final answer CF dot dr is equal to, just now you have 3 over 2 plus 13 over 6 plus 5 over 3. So you add up all of them. So you get what here? You get here should be 9 plus 13 plus 5, right? Over 6. Oh no, 10. 10. Okay. All right. Okay. Okay. All right. So what do you get here? 23. The same as what we calculated. I'm sorry, this one should be 2. I'm sorry, this one should be 2. Negative 2 here. You will get negative 2 here. Yeah, this should be negative 2. I'm sorry for this one. So if you try to compute this one using the line integral, the flow integral here, then you will get what we call here as the value here 5 over 3. This one should be 5 over 3. Okay, this should be 5 over 3. Baik. Okay, so then I just compare one to provide you some comparison between the line integral using directly calculated using flow integral and the flow integral using the Green's theorem. Okay, baik. Okay, so far so good. Hopefully you get the idea here. Any question you want to ask? No? So if no, let me continue. Let me continue. Okay, let me continue. Yeah, so I give you the mathematical insight of this one. So just like equation, so they are equal. Right. So now let me just give you some rough idea why this Green's theorem works that way. Why you have this circulation f dot r is equal to this one. Why you have partial q partial x minus partial p partial y dA. Okay. So just give you some rough idea why this works. So actually this is proven by English mathematician the Greens there, right? In the early 17th century there. He worked on electromagnetism there and then found something like this theorem. So, so, so what is the insight of this? So let me just give you some idea here. So you have this closed simple curve. See here. Okay. Okay. So you want to complete the flow integral of this vector field over this, what we call here the curve C close. Yeah, flow integral. So just another name for this one is flow, right? This one, if you dr is equal to what? By definition, this is just f dot t ds, right? C. So this is a flow integral. So if you recall from surface integral, you have flux, right? This is flow integral. So why we call it flow? Because you make a dot product between vector field and the tangent of the curve here. So how much the vector field is in the direction of the curve there. So that's why we call it as a flow. And then if you want to compare here, so what is this formula actually? So this formula, if I make it as what we call here this one, gradient of f here. I mean the gradient cross with the vector field here, and then you dot with the vector k here. Okay. So this is equal to partial q partial x minus partial p partial y. Okay. So this is what is the gradient cross f here? This is a curl, right? If you recall, this is a curl. Curl of f dot with k. So what is curl here? Somehow you measure circulation of a vector field there. Circulation of vector field. The direction of the circulation. Okay. Okay. So what we did here. So instead of you are calculating in the boundary here of C, so let me involve the region inside also. So let me make a partition like this one. You see that if you make the draw here, this line, this line, this curve. I mean this curve. You have this one, right? You go here. Okay. And then if I consider this one, I will go here, and go here. So everywhere here. So everywhere in the, I make a partition just now. So I can make it very, very small here. Very small, small partition. Okay. And then this one, you see that if you make this situation, so it will cancel each other, right? It go here, going back here, down, go to the right, go up here. But next time you go, here you go down, go to the right, but here go up here. You cancel out what you go down just now. So you will cancel something else. Always you cancel. Somehow that's the reason why you consider inside here similar when you consider in the boundary. So somehow this is a rough idea why you have that formula of this here. And how come this term? How come this term? You see that when I consider very small here, right? It's like a circulation there, right? Circulate there. It's something like curl of the vector field here. So how to compute the curl? You have this formula. The curl of F, which is this one, and then you dot with K here, you should get this term. So this one you have another way to write it as you get curl of F dot with K dA. Okay. So this is a special case of a Stokes theorem. I'm not sure if you learned before. So it's a special case of Stokes theorem, okay? All right, so just a rough idea what it means by the Green's theorem. Yeah, so yeah, I'm not going to prove it to you. Yeah. Baik. Okay, so far so good. Any question you want to ask? What's the time? Okay, okay. Do you have anything you want to ask? No? Okay. So if no question, so I just maybe do one more example with you, and then we can also explain some application of this Green's theorem, and not application, what use, one of the use of this Green's theorem. So let me provide you one example. Before I show you one example, so now you see that you have a Green's theorem, this what we call here circulation, right? What we call as circulation here, because the flow is in this closed curve. Okay, C closed, that's why you get circulation there. Just now you have flow, right? This is a flow integral, because you have a curve here, you have curve here, C, right? Into this direction. So if you have a vector field somewhere, so when you compute the flow integral, you compute the direction of C here, right? Tangent here. Example here, tangent here. Okay, tangent here. You take some angle there between them. That's why you get this dot product here. If it positive value, then somehow the vector field is in the direction of the curve here. If it's negative, against the curve here, right? If it's zero, then it's across, orthogonal to the curve in some means here. But since you have C is closed curve, okay, that's why you can call it as a circulation here. This is a circulation. F dot P ds. Yeah. Okay. Yeah. Well. Okay. So we call it as a circulation here. Circulation. So now, if you have the assumption for Green's theorem just now, let the C closed curve, simple curve, and also it is positively oriented, and then the derivative, partial derivative of the component of F is continuous on the origin bounded by this C, then you can use this formula. Okay, partial Q partial X minus partial P partial Y. Okay? R dA. And then I want to give you the formula of finding region R here using this flow integral, which is circulation. There's some relation there. So for example, if you choose our vector field to be what? For example, if your Q, make it F equal to, for example, let what? How to make it constant here? You can have 1, for example. This you differentiate with respect to X, you get 1. So I will have negative Y here, I plus xj, for example. Okay. So this is your P, this is your Q, right? Therefore, our P here should be, so our P here should be negative Y. Our Q should be X. So you differentiate this one with respect to Y, you get P sub Y is negative 1. Q sub X, you get 1 here. And then you can differentiate inside the formula here. Okay. So if I got this formula, R, you get 1 minus 1 here, dA, right? So you get 2 dA of R here. So if I pull out 2, surely you get area of R, kan? You get this one. So this is area of R. Okay, so this is area of R is equal to what? So you see that just now we choose our P and Q specifically here, right? P and Q here. Okay. So you see 2 of this one R dA is equal to the flow integral F dot dr, which equal to what? If you use in the differential form, you will have 0. So I will have, uh, let me write, we call it as negative y dx, because you have this negative y p dx, right? Plus x dy is q. So this is another way if you want to compute area. Okay, area. And then this is area, meaning you compute using line integral, and then you will divide by 2 then. Okay. Baik. Okay. Okay, good. Any questions so far? So you can use this one to find the surface, no, the area formula. This is area of R. Area R is equal to what? You divide by 2 here. 1 over 2. This, don't forget C here. C, circulation C, negative y dx plus x dy. Where C is boundary of R. Okay. Okay. All right. So far, okay? Clear this one? Any question you want to ask? So yeah, maybe I can show you one example why this one also helpful for us to compute area. So the simple example is to find the area of ellipse there. Okay. For example, if you have this ellipse, find area of ellipse. Okay. So that's 1, 2, 3. Can you hear me? Can you hear my voice? Yes. So my connection is not good here. Is it clear on your side? Am I still with you? Okay, if so, then we continue. Okay. Now you can still hear me. Right? Test 1, 2, 3. Can you respond? So before can we continue with this one, finding area, or we can take a break here? Do you want to take a break or we can continue here?
You can continue it, sir.
Continue? Okay. Okay, let me just continue. So how to find the area of ellipse using this line integral. So just now we want to compute line integral using double integral. But now for double integral, we use this line integral. You can use this formula, right? So ellipse. So what does ellipse looks like? So you have this equation, x square over, let me use in general, a square, right? Plus y square over b square equal to 1. So this is major axis or major axis. So let me make it the major axis on x here. So it will looks like this one, right? Okay. It will looks like this one. So this is A, this is B. X, Y. So how you can compute this area? Okay. One way is you use the integration lah. You use integration, right? You have this equation. You use integration, the usual area under the graph. You find this area first, and then you multiply by 4. But now that we use this line integral to compute this area, so the first things you need to do is you need to parameterize our C here. So let me consider it counterclockwise here. So how you can parameterize this ellipse? Okay, what is x, what is y here? So RT here, for example, is equal to what? X, you can have what? X I plus yj. So what is x, what is x, what is y? So x is equal to a cosine t. We can choose this one. Y equal to b sine t, right? So if you take square here, you get a square cosine square, right? You substitute here, you get a square cosine square, and then you can cancel out a square, the cosine square. And here you have b square sine square, which cancel out b square. You get cosine square plus sine square, you get 1. So this is one of the way to parameterize ellipse, okay? And then what nice here, if you want to make it counterclockwise, t should runs from 0 to 2 pi lah. 0. So this is how you parameterize lah. This is equal to a cosine t I plus b sine t j. This is the parametric equation that we use. Okay, now we need to substitute everything into this formula. Okay. So how to compute this one? So you have 1 over 2 c negative y dx plus x dy. You just find everything here. Okay. So what is negative y here? I mean, what is y, what is dx, what is x, what is dy? So here you have dx equal to a negative a sine t dt. Dy should equal to v cosine t dt. Okay. So this is equal to 1 over 2 from 0 to 2 pi. Okay. And then this is y is what? Y is b sine t. Dx is what here? Dx is this one. Negative a sine t dt. Okay. And then what is x? X is equal to a cosine t. And then dy is b cosine t dt. Okay. And then from here you simplify whatever inside here. So what do you get? 1 over 2, 0 to 2 pi. You get ab sine square t dt plus ab cosine square t dt. And then you can pull out dt there, right? So if I pull out dt and at, I will get 1 over 2 ab 0 to 2 pi sine square t plus cosine t square. Cosine square dt here. This one you can cancel out, right? This is identity equal to 1. And then you integrate 1, you get t. So you get 2 pi. So you will get 1 over 2 ab 2 pi. So the answer should be ab pi. ab pi. So this will be the area of ellipse. AB pi. Baik. Okay. So that's one of uses of this Green's theorem. You can compute the area under the graph. Area of some region. Yeah, area of some region using line integral. Yeah. Do you have anything you want to ask? So more or less, this is about the Green's theorem. So what nice is you have relation between double integral and line integral. So you see that, so what is inside there, if you have conclude later on what we call here vector calculus here, right? You will notice that there's some similarity there, okay? Some fundamental theorems. So if you recall again, what is fundamental theorem of calculus? You will have fx dx, right? If you differentiate from a to b, so if x here has antiderivative, okay, you just evaluate at the end point here, right? Okay, this is a fundamental term of calculus there. So what does it mean here? Meaning that if you want to know from the interval a b here, enough for you just to know at the boundary there. So this is what it means. So similar here in the line integral, for the Green's theorem here, you see that if you have, just now I have C f dot dr is equal to, so let me formulate the other way around. So you have this one, R, and then you have, just now I say curl, right? Curl of f dot k dA here equal to this formula, okay? So you see that you have, this is your C, inside here is your R, okay? Meaning that to know anything happen inside, enough for you to know at the boundary there. Always there's some relation there, boundary region here. So this boundary, the whole region here. So this is a boundary of R. Later on, if you look conclude about surface integral also, you have a solid there, a boundary of the solid also, you have some region there. I think you have divergent theorem, I think you will learn later. So that's what nice about vector calculus, especially for this Green's theorem. So it unified somehow some relation between boundary and also the region itself. Okay. Baik. Do you have anything you want to ask? So I think that's the thing I want to share about this theorem. Yeah. Or you want to do more exercises? So let me try to find one exercises in my book here. So for example, let me show you this example. Show you this example. Ah. So I give you this example. So let compute this one. Example. So compute this circulation x square minus y dx plus x square plus y dy. Okay. Where the C is boundary of two region circle here. Where C boundary of x square plus y square equal to 4 and x square plus y square equal to 9 here. Okay. Oh no, 1 and 4. 1 and 4. 1 and 4 here. Okay. C is the boundary of this one. Right. So we try to sketch first what you see here. So in another word, if you want to see here, so what is the form in f dot dr there? So this is equal to cf dot dr, where f is equal to, let me make it x square minus y I plus x square plus y j here. Okay. So this is our P, this is our Q here. Okay. So now try to have this one. And then what is the boundary? So you have circle, right? Here, circle of radius 1. And then you have circle with radius 2 here. So it should be this one, right? So you have this is not a simple enclosed curve. So C is not boundary of simple enclosed curve here. So we can apply directly. This one you can apply directly, what we call here Green's theorem. But here what you can do is, first you consider this is as your C1. This is your C2 here. So C here is consider of this C1 and C2 here. Okay. So meaning that you need to compute what? You need to compute first this C1 and then you add this one C2. How to do that? You will use the region between here. Okay. Yeah. Okay. Yeah, somehow it is out of the scope of this the green theorem. So this is has some manipulation here. You need to manipulate a little bit. So you need to have this is the counterclockwise, and then this one you have something. So let me just uh choose one of them instead of boundary here of two circle. Let me just show you this is the boundary of the C1 circle here. No need this C2 here. Okay. So I have this C1, C2. So make it simpler. That will directly equivalent assumption of our Green's theorem here. So, so I have this one, okay, boundary of this one. So let me just focus on simple and closed curve without what we call here manipulate some situation. So if you have this kind of situation, then you have a simple and closed curve. So right, because C here is simple and closed curve. And then from here, so how we can compute this one, the circulation here, the flow integral. So you can use what we call directly, you need to parameterize, right? How you parameterize C? Usually circle you parameterize as follow. RT is equal to 2 cosine T I plus 2 sine T J here. Okay. So you will get, this is a parameterization of this circle. So from here, you can find what is x, what is y here, right? X equal to 2 cosine t, y equal to 2 sine t. Okay. So here t runs from 0 to 2 pi, the whole circle. Right? Okay. So if you obtain this one, yeah, everything you can just substitute here. Just find what is y, what is dx, right? So y is already given and x already given here. So dx is equal to negative 2 cosine t, and then dy equal to 2 cosine t. So you will involve a lot of trigonometric integral later on. Okay. So you will get what? Your integral just now will looks like 0 to 2 pi. So just now your x square kan? X square minus y, you get x square is this one. 4 cosine square t minus 2 sine t. And then you have dx. dx equal to negative 2 cosine t dt. Forgot dt here. Okay. And the second part is what? This one, x squared plus y dy. So I will have 4 cosine squared t plus 2 sine t. X squared minus plus y. And then you have dy. dy is equal to 2 cosine t dt. And then you can simplify everything here. So what do you get here? You see, you will involve a lot of sine and cosine, right? Integral punya, the integral, trigonometric integral, I'm sorry, trigonometric integral here. 0 to 2 pi. Then you have this one is 2 cosine t, negative here. You get negative here. Let me just expand everything. So I have 4 cosine squared t. If you want to simplify, what do you get here? This one, you multiply this one, right? You get 8 cosine cube. Right? You get 8 negative cosine cube t plus 4 sine t cosine t. Okay, dt there. And then the second part here, plus, you get 8 cosine cube t also, plus 4 cosine t cosine t. And then you will get what? dt. Okay. So you notice that this can be cancelled with this one, right? So what left is just 0 to 2 pi. This add with this one, you get 8 sine t cosine t dt. Then you need to integrate this one. Okay. So what do you get here? So if you use the double angle of sine, you get 2 pi, you get 4 sine 2t, right? 2t here. Sine 2. Okay. And then you will get what here? The integrate, you should get 0 to pi. You can integrate now, right? 4 cosine 2t over 2, 0 to 2 pi. So you get what? Cosine 4 pi minus 2 cosine 0, right? You will get 0, right? You get 0 at the end. You get 0. Yeah, you get 0 at the end. So that's how you compute this using line integral. Okay. And then if you want to compare with Green's theorem, then you can try to compute using Green's theorem. So you find the pxy, and also qxy. You differentiate p with respect to y. You differentiate q with respect to x. Then you use the double integral to compute. Right? Okay. Baik. So if you want to use Green's theorem, then you will have what? Q sub x equal to what? Q sub x just now. Q sub x is equal to, this is P, this is Q. X squared plus y, 2x. Whereas P sub y, you get what? P sub y, negative 1. You get negative 1, right? Negative 1. Negative 1. So if you want to compute just now the circulation, is equal to the region here R, which is our x squared plus y squared equal to 4. And then you have this minus this one, right? 2x minus minus 1 dA. Okay. So what do we get here? You will get this circle. So the region here, let's make it as follow. X squared plus y squared less than or equal to 4. 2x plus 1 dA. Okay. This one, I think we can use what we call polar coordinate. So you can use polar coordinate 0 to 2 pi, 0 to 2 here, right? The circle there. Find the limit for polar coordinate. Then you have 2 r cosine theta plus 1 here. R dr d theta. Okay. Right. And then if you try to compute this one, you should get 0 also. You should get. Should we get 0 here? Let me check. Okay. So you have 0 to 2 pi. 0 to 2 of 2r square cosine theta plus r here. Dr d theta. Okay. It should not go to zero, right? You have 1 here. Why? I think I made some mistake somewhere. So if you integrate this one, cannot be 0, right? Because you have this 2 here. Yeah, let try to continue. Integrate 0 to 2 pi. Then I will have 2r cubed over 3 cosine theta plus r square over 2. 0 to 2 d theta, right? Yeah, it's not 0 here. I think I made some mistake here. 0 to pi, and then I will have, this is 8/16 over 3 cosine theta plus 4 over 2, which is 2. Okay, d theta. Yeah, this one is 0, correct? Right? 16 over 3 cosine theta d theta plus 2 d theta here. This one is 0 is correct. I think this is 0 because you have sine there. Sine 0 and sine theta is 0. But here I don't get 0 here. So I think I make some mistake somewhere. Yes. Make some mistake somewhere. Or maybe this one, I'm not sure. P, Q, 2x minus 1. Should be 2x minus 1 here. Two x minus 1, right? If I use Green's theorem, I should have, this is our P, this is Q, 2x, P, Q, 2x minus 1. So I will have this correct formula here, 2x plus 1. Or maybe I make some mistake somewhere here in my computing this line integral. By the way, do we have still time?
Wait. I will find it.
Hmm?
Uh, I think we have same example for this example.
I see. Okay. All right. So I think for Green's theorem, more or less, I think is correct formula. I wrote it here, right? This is, if you use polar coordinate, I will have this one. Maybe I need to recheck again. This R cosine is correct. We need to recheck again this one. Maybe I make some mistake somewhere here. So let me do it again. Just to finalize. Okay. Whether this one. If not, then I think I do some wrong question. I mean wrong formulation everywhere. So I have a circle now, right? So yeah. Come back again to the original question here. X squared minus y, x squared plus y. So I have C is given by the boundary of this one, x squared plus y squared equal to 4. Okay. So how I can parameterize this one in the counterclockwise direction? So if I want to compute directly without using Green's theorem, so I need to parameterize C. So my C should be given by x equal to 2 cosine t, right? And then y should be 2 sine t. And then, yeah, if I use this one, if I take square, I get 4. Yeah, then I get 4 here. Okay. And then dx should be negative 2 sine t dt here. Whereas dy should be 2 cosine t dt. Okay. Now I need to substitute everything here. So let me compute one by one. So if I do this parameterization, t should run from 0 to 2 pi, right? T should run from 0 to pi. So t should from 0 to 2 pi. So this is t equal to 0 here, and also it equal to 2 pi there. So now maybe I need to look one by one these things. So x squared minus y dy should equal to what? X squared is this thing, 4 cosine square, minus y should this one, 2 sine t, right? And then I have dy. dy is 2 cosine t dt. So yeah, then I will multiply. I will have 4 cosine, no, 8 cosine cube t minus 4 sine t cosine t dt here. Okay, this is the first differential part. The second differential part is this one, x squared plus y. This one should be dx, right? Why dy? Dx here. I'm sorry. This should be dx. Dx should be negative. I'm sorry. Negative 2 sine t dt. So I have negative here, and then I have positive here. Okay. And then for x squared plus y dy, the second differential part, this one. So what do we have? So kita akan ada this square should be 4x squared, should be similar just now. Cosine square t minus y should be plus, not minus, plus 2 sine t. And then you have dy. dy is 2 cosine t dt. Okay. And then just simplify, I will get 8 cosine cube t plus 4 sine t cosine t. Okay, dt then. Okay. So if I add up these things,
Ah, no, sorry. Uh, for the x square minus y is dx is still, I think it's still wrong here. It should be minus 4
This is,
cos square t sine t.
I'm sorry, which one? This one.
No, the right one, the right.
This one.
Yes, below.
This one.
Yes.
This one should be
Minus a cos square sine t.
Okay, cos square sine t here, right?
Mm-mm.
Yeah, thank you, thank you. Why I make it cosine cube there? Yeah, I made mistake there. Silly mistake. Should be cosine square t sine, right? Sine t here.
And the second is for sine square t.
Yeah, for sine. Yeah, thank you very much. Yeah, this one with this one, right?
The above.
This
Yeah.
one.
Yeah.
Yeah. Yeah, I think I feel, I'm not sure. I cannot think correctly now. So sine square here. So I have sine square t. Okay, you have sine square t here, everything. And then this one should be correct. Cosine cube, cosine sine. Okay. Ah, yeah, I cannot cancel then, right? I cannot simply cancel everything. So I will have x square minus y dx plus x square plus y dy should equal to, thank you very much for your help just now. So I will have negative 8 cosine square t sine t plus 4 sine square t plus 8 cosine cube t, and then plus 4 sine t cosine t dt just now, right? Now I cannot simply cancel just now. Maybe I'm eager to cancel everything, so that's why I make some miscalculation. So you see that now you need to integrate this one. So if you have integral 0 to 2 pi, then this one should be, C here, this one 0 to 2 pi dt, right? So you involve many integral here, right? You need to integrate this integral. This one you can use substitution here. So you have four integral you need to deal with. 0 to pi negative 8 cosine square t sine t dt. Then you need to plus with 0 to pi 4 sine square t dt. And then you need to plus 0 to 2 pi 8 cosine cube t dt. The last one should be 0 to 2 pi 4 sine t cosine t dt. All of them is manageable. You can compute it, either use substitution or identity, but have a lot of integral you need to deal, right? 1, 2, 3, 4 integral you need to deal. Compare, if you try to compare this one, compared to when you use Green's theorem, so you use this one, so you only have one integral you need to deal, and then this is not somehow difficult to integrate. So what do you get here at the end? This one, some more or less you get. If you want to compute it, you get this answer of this one. Should be
For B. Yeah. For
4.
B.
Yeah, 4. Yeah, 4. All right. So more or less, if you compare with this one should also get 4 by here. Okay. Yeah, that's what I want to show you. Example. Why we have this? Why green zero help us in a large way? Okay, in large way to simplify our calculation. Yeah, I think I can stop here maybe. So that's a little bit on Green's theorem. Do you have any question you want to ask? No? So yeah, thank you very much. So for any shortcoming, so thank you very much for your listening here. I think I can
Okay.
stop share, right? Can I stop sharing my screen?
Yes, Dr. Al.
So first, let me stop sharing. So that's it for my sharing session. So I really appreciate for your listening and really appreciate and apologize if there are a lot of shortcoming. Yeah, yeah. I pass back to you. Dr. Jovian, ya, yang pertama.
Okay, thank you very much, Dr. Mohd Ali Khameini Ahmad, yeah, for the insightful lecture on Green's theorem today. Okay, we truly appreciate your time and willingness to share your valuable knowledge and academic experience with our student through the UGC program. Yeah. I hope today's lecture has helped our students gain a deeper understanding of Green's theorem, yeah, and its role as one of the fundamental concept in vector calculus. Yeah, hopefully, yeah, this session also motivates students to further explore the beauty of and the application of mathematics in various scientific fields. On behalf of the Department of Mathematics, Faculty of Science, Mathematics and Mathematics, Diponegoro University, I would like to express our sincere gratitude for your kind contribution and collaboration. Yeah. We also sincerely hope that this collaboration between Diponegoro University and Universiti Teknologi Malaysia, will continue in the future through more academic activities, research collaboration, and international programs. Okay, please accept our apologies if there were any shortcomings or inconvenience during today's session. Okay, to all students, thank you for your participation through about guest lecture session. Okay, finally, let us give one more applause to Dr. Mohd Ali Khameini. Ya, tolong aplausnya guys buat uh,
Thank you very
Dr.
much.
Ali ya. Terima kasih semuanya.
Okay, so
Thank you everyone. Ya, oke. See you in the next program ya. Stay curious and keep learning. Wassalamualaikum warahmatullahi wabarakatuh. Oke, good afternoon everyone.
okay, okay.
Thank you Dr. Ali.
So I may leave, right? Okay. So thank you
Ya.
very much. See you again later, maybe in the future. Okay.
Halo, Kak.